looks like it worked.
Yeah, great. All right. So I think, yeah, it's a few minutes past the hour, so it's a good time to get started. So welcome everyone to the first One World Probability Seminar of fall 2022. Me and David Promol, who's also here on the call, are the organizers this term. And we're very happy to have Sam Punshon-Smith from Tulane University give our first talk. And he'll be speaking about using regularity to estimate Lyapunov exponents. So I'll hand it off to you.
Thank you. Yeah, it's a real honor and pleasure to be here for the first talk of the semester. And let me say good morning, good afternoon, good evening, good night, wherever you are. It's early in the morning here. Right, so I'm going to talk about a recently developed method, relatively recently, building on a very large body of work studying Lyapunov exponents for diffusion processes, particularly hypoelliptic diffusions. And all this work is mostly, although we have some sort of separate pieces with different collaborators here, is done with two of my close collaborators, Jacob Bedrosian, who's at University of Maryland, and Alex Blumenthal, who's at Georgia Tech. Jacob is sort of an expert in partial differential equations, and Alex is an expert in dynamical systems, particularly random dynamical systems. So let's start at I'll keep it slow in case people are still rolling in here. So basically, I want to study. I'm very interested in studying chaotic dynamics, and so in general, many systems are observed to be chaotic physically. And what does chaos mean? Well, it's not really a super well-defined concept, but in general, you could say that it's characterized by some extreme unpredictability or extreme sensitivity with respect to initial data, making any sort of long-term predictions very hard. So it's a very unstable type of system. Famous examples of let's say some of the first discoveries of chaotic systems were the Lorentz 63 model, where Edward Lorenz was actually trying to study atmospheric motion and convection and created a really simple model, and was running it on two different computers and got completely different answers because there were rounding errors that were completely destroying everything. But also things in sort of the three-body problem, famous work by Poincaré on the homoclinic tangle. You could argue is maybe some of the first discovery of chaos, but also there's many observations of it. If you swing a double pendulum, a double hinge pendulum, it's something you see. It sort of randomly flips around and behaves really erratically. But more so, I mean, much of the study of chaos now actually came initially from motivation of studying turbulence in fluid mechanics, one of the extremely hard, extremely challenging problems that to this day is still not really well understood, especially from a mathematical perspective. So one of the things you see is that in extremely high dimensional systems, so you could think fluid mechanics, but you could also think nonlinear waves, plasma physics, or even just, in systems related to economics, they're typically observed to be incredibly chaotic. Yet it's not very easy to know how to prove this. So this Lorentz 63 example I wrote down explicitly. You may or may not have heard of it, but it's a very, very famous example, and at least you've probably seen the picture before of the attractor. So what is a Lyapunov exponent? Particularly, what does it mean to have a positive Lyapunov exponent? So here, let's consider some dynamical flow on a manifold that gives rise to some time evolution for some initial point on there. And we consider the top Lyapunov exponent to be the exponential infinitesimal sensitivity of this flow with respect to perturbations in the initial data. So if I differentiate the flow and look at its asymptotic logarithmic growth, I define this to be the top Lyapunov exponent. And in particular, if that rate is positive for almost every, and with respect to some measure and being a little loose, or at least on some positive measure set, this is considered to be a signature or a strong sign of chaos. So in particular, I'm going to take this to more or less be the definition. If you have a positively Lyapunov exponent, you are chaotic. However, proving that you have a positive Lyapunov exponent is a notoriously hard problem, particularly for deterministic systems. So it's only known for very specific systems. So for instance, Lorentz 63 was, the example I showed before. It actually has been proven that it is chaotic, although the proof is not simple. It's computer assisted and uses sort of computational methods to compute normal forms. But there are many other sort of toy models related to discrete maps and so on, axiom A systems, contact NSL flows, and so on, that are almost by construction designed to have a positively Lyapunov exponent. And in those cases, the axiom A contact NSL flows, they are known to be uniformly hyperbolic systems. And this means that the linearization has a nice action that splits the tangent space into an unstable and a stable direction. And on the unstable direction, you have sort of expansion, and on the stable direction, you have uniform contraction. The problem is that many systems of interest don't have this structure. And so you lack a uniform hyperbolicity. You don't have a clean splitting. There may be something in it known as non-uniform hyperbolicity, but this is extremely hard to get a handle on. And let me just give you a picture of what it is that makes it so hard. So a really famous example of a relatively simple system that is observed to be chaotic, at least on a very large measure set, is what's known as the standard map. So this is a discrete time dynamical system that's being iterated, and it's really just like a stroboscopic section, I think, of what's known as the kicked rotor. So this is sort of a little rotor hanging in gravity that you just periodically kick with the same frequency, and P is the momentum, and theta is the angle of the rotor. This is actually a Hamiltonian system, so it conserves the particular energy. And what you're seeing here in this picture is the positions of all the orbits, so where things sort of went and end up after repeated iteration. So a fixed color is typically a fixed orbit. Of course, they ran out of colors, so you see lots of repeat orbits. But what you see here is what's often referred to as a co-mingling of dynamics. So there are regions where you have lots of periodic orbits, just things that are going around in circles and repeating themselves. But you have periodic orbits nested within periodic orbits. These are, related to KAM tori. But also, what you see here is that in the bulk you have this fuzz, which is essentially, a chaotic region. If you start off in there, you just dance around in this big, essentially positive dimension or positive measure set. And it's very unpredictable, and you kind of mix and actually end up all over the place. So it behaves almost randomly there. But if you look, you see that the space is nested with lots of little periodic islands, and they're known as elliptic islands, and they're kind of fractally embedded in the space. And so it's actually very hard to separate yourself from the chaotic and the non-chaotic regions. And what typically happens is that when you're in the chaotic region, if you're really close to an elliptic island, those elliptic islands can twist around your cones of contraction or stretching that you would normally get, where you would say that you have a positive Lyapunov exponent. It twists them around according to these periodic orbits, and can kind of mess things up. So I'll give you some more examples of what that means in a second. However, if you add noise, it can help a lot. So you can, in some loose sense, recover uniform hyperbolicity. So in fact, Alex Blumenthal, one of the collaborators, he actually has a proof that if you add just a little bit of noise to the standard map every iteration, just a tiny amount, that you can actually recover positive Lyapunov exponent for this. And essentially, it shows that you don't get stuck in the really sticky elliptic islands. You end up leaving some of the bad sets. Moreover, one of the really nice things, the second you have noise, it very often gives you something known as the multiplicative ergodic theorem. And this theorem essentially tells you not only do the Lyapunov exponents that we defined before, they exist, but they actually exist in they exist for almost every x, and they're deterministic numbers. So they don't depend on the noise or actually the initial data. But not only that, it actually implies the existence of more or less a splitting of spaces where you do have asymptotic expansion and contraction. So this is a very important result of having a little bit of noise or ergodicity. It actually recovers in a loose sense hyperbolicity. But the main thing is that these pathological effects, the cones being twisted around, or this co-mingling of dynamics, that you can roughly show that they're sort of probability zero events. Okay, now let me just give you, it's a really simple discrete example to sort of see how this might work. So let's consider a Markov process on the space of determinant one matrices in 2 dimensions. And they're just given by IID matrix products. So just take eta here to be a law on SL2 or some, and we just randomly IID sample these matrices, take a product of these n matrices long, and define this to be a superscript n. This is a Markov process on this Lie group. And back in '68, Furstenberg actually came up with a very remarkable theorem at the time, which sort of showed that if I study the Lyapunov exponent for this, essentially what is the asymptotic exponential growth rate of this? Well, it is typically or generically positive. And you can study this sort of via group properties of the support of the measure. So if I look at the support of this law, and I look at the smallest closed subgroup that contains the support, so I sort of look at, I let the support of the generate a larger group. If that's SL2, I mean, he had a slightly weaker statement than this, but let's just for now keep it at a slightly stronger statement, that if this is actually equal to all of SL2, then there exists a positive Lyapunov exponent such that this thing converges almost surely with respect to this measure. Okay, and so what it's saying is that if I'm supported, if my law or these linear products are supported on enough of this Lie group, then in fact you have a positive Lyapunov exponent. One of the negative examples for this, for instance, is if the law is only supported on just rotations or shears, it's clearly a zero Lyapunov exponent. One of the other examples, though, is that if I do a random Bernoulli trial where with probability 1/2 or with probability p, I pick a something which is a hyperbolic stretching, and then with probability 1 minus p, I pick a rotation which exactly flips me from the stable to the unstable. In fact, that will give you with probability 1 a zero Lyapunov exponent, as long as p is not equal to 0. So in some sense, he gave a sharp condition for this. So what we're going to consider here is hypoelliptic diffusions. So let's consider a stochastic differential equation on a manifold, which is given in Stratonovich form like this. So these xk's are just smooth vector fields on the manifold, and the wk's are just IID Wiener processes on some canonical probability space. And I'm going to assume for now that there's some global stochastic flow on this manifold. So maybe there's some Lyapunov function for it. The manifold could be unbounded, for instance. And it defines a measurable random dynamical system with respect to the Wiener shift. So the Wiener shift specifically, I mean, is if omega is the canonical Wiener space, so the space of continuous paths, then the Wiener shift just shifts the paths forward in time and then resets the value at t equals 0 to 0. And it being a random dynamical system essentially says that this mapping defines a measurable mapping on the product of the manifold cross omega, and it satisfies this property here, which is known as the cocycle property, which more or less says that it factors into that at time t plus s, it factors into two independent maps. These are diffeomorphisms, and so you can think of any flow coming from a diffusion process, or more generally a Markov process like this, to be a product of independent random diffeomorphisms, or a composition of random diffeomorphisms. So more generally, in this case, the generator for this Markov process, as is well known, it's just given as this differential operator, where here x0 I'm viewing as a first order differential operator, and xk squared, the noise vector fields are, it's a second order differential operator because I'm squaring here. And I'm going to assume that this diffusion is hypoelliptic, and I'll get a little bit more into precisely what I mean by that, but for now, for all intents and purposes, let's just assume that this means that there is a unique, smooth, stationary measure for this Markov process. Call it mu, and it has some density rho that is smooth. In particular, the rho here satisfies this hypoelliptic PD, where L star is the adjoint of the generator. Okay. Under those conditions, this measure mu is actually ergodic. And under very mild moment conditions that I'm not going to write down, we have the multiplicative ergodic theorem. So very specifically, it states that the derivative of this flow exists, this limit of the derivative of the flow exists, and it's equal to this top Lyapunov exponent. And this limit exists P cross mu almost surely. And moreover, we can also look at the determinant of this, and this thing converges to the sum of the first n Lyapunov exponents, which I'm not going to talk fully about the entire Lyapunov spectrum here, but for really what we need here is just we need the total sum of the Lyapunov exponents, which is related to the net volume compression or expansion in the system, and lambda 1, which is just related to sensitivity. Okay, so what we'd like to do is somehow estimate these quantities. So there are many works on this, okay, that somehow can relate Lyapunov exponents to properties of diffusions. So just to name a few people, many works in the random dynamics by Ludwig Arnold, Baxendale, Harver-Hill, Bougueral, Le Drapier, Ly-Seng Young, and many other people. What I'm going to focus on specifically here is a subclass of models that look somewhat like the Navier-Stokes equations, but they're finite dimensional, but arbitrarily high dimension. Okay, so let's consider a class of bilinear models that look like this. So this is an SDE with a bilinear nonlinearity, and it has some positive definite dissipation. It's like the Laplacian. This is sort of a model of the Navier-Stokes equations. And then we add some noise to it, where we have some epsilon in front of the dissipation, and we take square root of epsilon in front of the noise. This is a natural sort of small noise scaling, sometimes referred to as fluctuation dissipation scaling, where you scale down the noise and the dissipation by roughly the same amount, and so that if you were to look, for instance, take the square of the magnitude of x, the amount of dissipation and the amount of energy being pumped in would balance under this type of a scaling. And we're going to assume that the noise directions that we pick, they're just constant vectors. They're linearly independent. And moreover, this bilinearity, we're going to assume it conserves volume, which is what, for instance, happens in the case of the Euler equations. And it's also energy conserving, which means that let's say if I only took the equation x dot equals b of xx, that it preserves the magnitude of x. So everything for that deterministic equation is constrained on the sphere. So examples of systems like this are many. If you take Galerkin truncations of the Navier-Stokes equations in 2D or 3D, you project them in Fourier space, this is exactly it. So if I was to simulate Navier-Stokes on a computer, this is exactly the model. Other interesting ones actually are, you don't have to take Galerkin, you can take other approximations. So for instance, in 2D Euler, there's a very nice approximation of the Euler equations on the special unitary group that preserves much more of the Euler-Poisson and structure in the Casimirs. But also, there are other models. So, people frequently study in fluid mechanics, the shell models, and the Lorentz 96 equation, which is not the same thing as Lorentz 63 equation. It's another sort of toy bilinear fluid model. And almost all of these systems are viewed to be chaotic, but only when you take epsilon small enough. So at a certain point, there's a sort of a bifurcation structure. If epsilon is big enough, this entire system has a one-point attractor, or the sort of one force, one solution principle. And then as you take epsilon small enough, that loses stability, and eventually you end up with a chaotic attractor in a positive Lyapunov exponent. And so we want to understand when that happens. So let me just give you a rough idea of what is we're looking at. So particularly for the Navier-Stokes equations. So these are some numerics I ran. Hopefully you can see it on Zoom. I don't know if the sampling is going to look so good. But on the left here, this is the vorticity field for Navier-Stokes. This is with white and time noise. And on the right-hand side, we're actually looking at its linearization. And so what you can see actually is that in all the regions between the vorticity, the linearization is extremely strong and peaked. And has, but it's a huge mess, as you can see. But this is a very chaotic system, and we're not even in an incredibly chaotic regime. But it's also very rich. There's a lot of structure there. Okay. Okay, so what we want to do here, in fact, a really important role is played by not just the hypoellipticity of the SDE, but the hypoellipticity of its linearization. So let's just stick with the bilinear model I gave you. In a second, of course, much of what I'm saying actually applies to general hypoelliptic SDEs. But let's take the derivative of the flow. This defines a matrix, so this is in GLN. And in fact, the linearization here solves this linear ODE on GLN, because the noise in our case was additive in the model, so that when you take its derivative, it goes away, and we have this linear equation. And suppose I say that the original thing was hypoelliptic. Now, by that, I specifically mean that if I take the drift vector field for the bilinear model, and then I look at the Lie algebra generated by these vector fields, namely the first commutator of the Lie bracket with the noise direction and the drift, and then all the noise directions. This is a Lie algebra associated with sometimes what's known as the parabolic Hörmander condition. It plays a strong role in not just regularity of stationary measures, but also uniqueness and controllability. If we define this Lie algebra, then for every x, we also define an analogous matrix algebra. And what this is that for every x in that Lie algebra, I look at all the vector fields that vanish at the point little x, and then I linearize those vector fields. I take the derivative. So this defines now a matrix in SL n, because if I subtract off the divergence like this, I get something which is traceless. And so this, you can show, is actually a Lie subalgebra of SLN for every x. And so we say that this thing is sort of matrix hypoelliptic if for every x, the original Lie algebra spans the tangent space if I evaluate all the vector fields at a point, and if for every x, this matrix Lie algebra is equal to SLN. This is like an infinitesimal version of the Furstenberg condition I gave you before for Lie algebras. Then this actually says that this joint process XTJ, suitably normalized by its determinant, is hypoelliptic on this space. Now, what does that mean? Well, in fact, so here's the main theorem, or let's say one of the main theorems. So we showed, in fact, that if we have sort of three conditions for that general model, namely, if we have hypoellipticity, if we have matrix hypoellipticity, and I'm being a little soft here, that they have to be hypoelliptic in a way that's uniform in epsilon. So not only do they have to span, but I need to be able to choose vector fields in a way that don't depend on epsilon. But that's not particularly bad. And moreover, if there's one non-degeneracy condition on the bilinearity, namely that I can, on the noise directions I'm forcing, if it cancels on them. Okay, so for instance, if these are Fourier modes and B is Navier-Stokes, this is equal to 0, because Fourier modes are stationary states of Euler. This is a very well-known condition, for instance, in controllability. People like Jonathan Mattingly, David Herzog, and Nathan Gladholz have some works on this, and you see that this is a very important condition. Essentially, it shows you that the nonlinearity is effectively odd degree, which gives you uniqueness of a stationary measure. But once you have these three conditions, then our main theorem says the top Lyapunov exponent, if you divide it by epsilon, goes to infinity as you send epsilon to 0. So what this means in particular is that if you take epsilon small enough, eventually the Lyapunov exponent has to become positive. Okay, it's not the most optimal condition, and the reason is that we're not using a huge amount of information about Navier-Stokes, because that sometimes is a little too hard actually. But nonetheless, it's a really robust thing in that it's saying that for a system like this, and in fact, there's much more general ways to view this. You know, chaos is or having a positive Lyapunov exponent is actually hard to avoid. Okay, and you can sort of show this, especially if you have hypoelliptic diffusions. So let me just comment on the proof strategy here. So there are two main steps. The first step is that we're going to study something which we'll call projective regularity, and I'll explain a little bit more about that. It's going to be a consequence of the matrix regularity. And from that, we're going to use a quantitative sort of regularity estimates and Fisher information. So the Fisher information ends up playing a very important role in our work. It has analogs with stuff that's already very well been known relating to Lyapunov exponents with entropy and relative entropy. Yeah, so we have this Fisher information identity, and there's going to be a very specific quantitative lower bound on the Fisher information that we can get from the hypoellipticity assumption. But in order to do this, it requires checking an extremely hard Lie algebra condition. So in fact, that matrix Lie algebra property is something that is not easy to check in general. If you have a model of interest, it takes quite a lot of computation in some sense. In some ways, it's not really even possible to do by hand in most systems of interest. But once we do that, the next step is we take a zero noise limit. So once we have these quantitative estimates, we can send epsilon to 0 and actually obtain a limiting measure that has to be absolutely continuous on a certain space that we can show then has to actually have concentration. So there's some contradiction going on. And the thing that breaks the contradiction is that you have a positive Lyapunov exponent. So I'll go into more details about that, but roughly there are two pieces of it. One is get quantitative estimates, two, send epsilon to 0. All right, so let me just comment here on getting sufficient conditions for hypoellipticity in the case of the Navier-Stokes equations. So those two conditions I gave you were very abstract, but in fact, they're more practically checkable if you have a bilinear thing like this. So for instance, hypoellipticity, you can try to check by taking first the noise directions, then plugging them all into the nonlinearity and looking all the new directions you get, and then repeating and so on. And if you eventually span your entire space, then you're done. That is more or less well understood for the case of the two-dimensional Navier-Stokes equations by the original work of Mattingly and then later works by Heyer and Mattingly. But the matrix hypoellipticity case is a little bit more tricky. Namely, if we define this matrix, this family of matrices HK, which are indexed over the noise directions, then this is something that we get by taking the Lth component of B evaluated EK EL. So this is more or less taking the linearized Euler equation and splitting it up into its sort of base pieces. And so these matrices here are all SLN matrices, but they're very complicated. They couple many modes. They have they're kind of banded matrices, and what you'd like to show is that the matrix algebra generated by this gives you all possible traceless matrices. The first one, like I said, is checkable by hand. The second one is very hard to check by hand for many models. If you have things that couple locally in frequency, like this Lorentz 96 model, you can do it, but otherwise it's hard. So let me just mention for the Navier-Stokes equations, these take a very specific form. So for instance, for 2D stochastic Navier-Stokes, we can write it in vorticity form in the following way. So the vorticity omega is just the amount that the velocity field is spinning. In 2D, that's a scalar quantity because it just points out of the page. So call that scalar quantity omega. As it turns out, in 2 dimensions, The vorticity is just advected by the flow and then diffused by this, where the flow is recovered from the vorticity again by this law, which is known as the Biot-Savart law. And then what we do is we're interested in a finite dimensional case, so we truncate it in Fourier space. We expand everything in Fourier and then chop it off on a lattice of this size here, where it's just a little square. And so this equation you can think of as posed on sort of complex coefficients indexed over the lattice. And in the Fourier space, the bilinearity actually takes this form. So it's the sum of all indices on the lattice J and L that sum up to a particular value K. So this is really just a discrete convolution, actually. And there's some coupling coefficient here, which is related to geometric interactions of these modes. So if J and L, for instance, are pointing in the same direction, or they're collinear, then this coefficient is 0. And if they have the same length, then this piece is 0. But apart from that, it kind of tells you that all modes interact with all other modes, which is one of the things that makes the Euler equations and the Navier-Stokes equations so challenging. And what this is, since the work of Heyer and Mattingly or Mattingly before that, they gave very nice conditions, almost sharp conditions, on when the noise is hypoelliptic for the Navier-Stokes equations itself. So namely, if you force a set of modes K0 for the Navier-Stokes equation, sorry, that's the set of modes K here, then you can try to construct a larger set of modes that come out of it that roughly treat it as an additive group. So I mean, what you say is take all the modes and then just try to generate as an additive group, except you have this one constraint that this coupling constant can't be 0. If they're 0, then they don't interact. And what you end up getting is this sort of, I can define recursively this set of indices that you try to generate an additive group under this condition. And eventually, if that gives you the whole lattice, then you say it's a saturating set. And in particular, that noise will be hypoelliptic. However, for the Navier-Stokes equations, the H matrices that I had mentioned before take this very particular form. They take the coupling constant here, but then they have this band of all the different Fourier modes that they couple along it. And if you start taking commutators of these matrices, which you can start doing by hand, you see that this is some algebraic expression of the Fourier variables. It turns into Fourier multiplier soup. It's a huge mess, and it gets really complicated the more and more brackets you try to take. However, if you give up trying to do it by hand, there are ways to use computational algebraic geometry and Grubner bases to show that this actually works. So we have the following theorem. This is just with Jacob and I, that if you take n big enough, and it's arbitrarily large, as long as it's bigger than 400, say, and it can be a bit smaller than that, then the Lie algebra generated by these matrices is actually equal to SLN. And therefore, if you have a saturating set for 2D Navier-Stokes, Galerkin Navier-Stokes, you have a positive Lyapunov exponent. Okay, and I'll comment, if I have time at the end, we'll see, I can comment a bit on the proof of this, although it's very algebraic, so it might not exactly be the right audience here. Okay, let's so in the remaining time, I want to talk about the actual regularity method. So how does this work? Okay, so we have a hypoelliptic diffusion. So let's just work in generality. Hypoelliptic diffusion on a manifold. One of the things that's quite easy to see is that if I take the sum Lyapunov exponent, remember this is the asymptotic exponential growth rate of the determinant of the derivative, then just by essentially Ito's formula and the ergodic theorem, this formula is actually related to the integral of some quantity here, which is just just Liouville's theorem more or less with some Ito corrections. So that's related to the average of the divergence with respect to the ergodic measure. And one of the interesting things that you can realize about this is that this quantity, this integral, if you use the fact that this measure actually solves this hypoelliptic PDE, you can relate this integral directly just by sort of an integration by parts to this Fisher information. Okay, so this integral of xk star, being the adjoint, rho here is equal to this integral of Q. All right, it's a fairly simple calculation. It just take this PDE L star rho and multiply it by log rho, and then integrate by parts a couple times, and you get this identity. And from this formula here, this sum Lyapunov exponent formula, this tells us that the Fisher information is equal to the negative of the sum of the Lyapunov exponents. Okay, now for most things of interest, the Fisher information is a non-negative quantity, so the sum of Lyapunov exponents has to actually be a negative number, or the negative sum of the Lyapunov exponents is non-negative. Okay, and so the key strategy here is that based on that sort of toy model I gave you, and this idea of cone twisting, one of the things you might realize is that we really need to keep track of where the linearization is pointing. If you don't, then you might have these sort of crazy examples where you twist onto these stable directions after being on an unstable direction for a while. And so if we try to track tangent directions, what you do is this is equivalent to lifting this process up to the projective bundle. So what this really means is that we're going to take our process and we're going to augment it with another process V, which is more or less just the linearization in a direction V normalized. Okay. In fact, that was the video I was showing you on the right. That was the linearization, then I just made sure to normalize it so it didn't blow up or decay, because it'll inevitably start growing or decaying exponentially. And so this augmented process defines a flow on the projective manifold. It's a lifted flow, and it defines its own RDS actually. So there's naturally another SDE that's just a canonical way to lift the original SDE up to the projective bundle. In these lifted vector fields, it's more or less there's a Lie algebra morphism that takes any xk up to some xk tilde, and the xk tildes here are just defined by taking the original xk and then augmenting it by derivatives of the vector fields, but then projected back to the tangent space of, let's say, the unit sphere. If you're not familiar with projective space, it's just the space of all one-dimensional subspaces. But if you like, you can think of it as a unit sphere, because that's just the double covering of it. Okay, so one thing to realize is that in projective space, there's tons of compressions and expansions. So even if the original dynamical system was volume preserving, the projective one is compressing and expanding all over the place. So for instance, if this was a saddle that I originally had, I'd be compressing here and expanding here. On the sphere, the linearization or of this linear flow, or the normalization of this linear flow, it gets repelled from stable directions and attracted to unstable directions. Okay,
sorry, what is Sx of m? Sx of m.
Oh, did I write Sx? Oh, I'm sorry. That should be a P. I mixed this up with some other thing I had. Let's call this Px of m. So this is the projective space as a tangent space, or for the projective bundle. S could be the unit sphere if you like.
Thank you.
Okay, so so one of the things that's useful to look at here is these. If I assume that these lifted vector fields are also hypoelliptic, okay, in the sense that they satisfy Hörmander's condition, and let's say that any ergodic stationary measure has this density. Okay, so we call the ergodic stationary measure for this process nu, and it has some density f. So then this hypoellipticity, I should mention, does follow from this matrix hypoellipticity. Okay, so this is just some transitive action of Lie algebras. But more generally, if I decide to study the Lyapunov exponents of this lifted process, it turns out that it has the following set of Lyapunov exponents. And this can be kind of viewed intuitively. First off, these lambda 1 to lambda n, these are just the ones associated with the original base dynamics. So this is the Lyapunov spectrum. But in fact, the higher up Lyapunov exponents, when I normalize the dynamics for linearization, it actually subtracts the largest Lyapunov exponent from all the other Lyapunov exponents. And so the full Lyapunov spectrum of this lifted process is given by these. And so therefore, if I take the sum of Lyapunov exponents of this, I get something that looks like 2 lambda sigma minus n times lambda 1, because I subtracted lambda 1 n, or let's say n minus 1 times, but I can add and subtract another one. And so if I apply the Fisher information formula I gave you again to this lifted RDS, I get the following formula. It tells me that the Fisher information for the lifted projective density is actually equal to n lambda 1 minus 2 lambda sigma. Okay, and now we have a nice formula. The original one for the Fisher information only related to the sum Lyapunov exponents. Now we have a formula that relates some non-negative quantity to lambda 1 minus some sum of Lyapunov exponents. So we have a little bit more information on lambda 1. And it's a signed bit of information. So I will remark that this formula more or less has been known by other people. I mean, Furstenberg more or less used a version of this in his original work. Baxendale has a whole series of works on proving this for stochastic differential equations. However, it's not done through the Fisher information. It's done through the relative entropy. So what Baxendale and Furstenberg more or less showed is that if I look at this measure and I push it forward under the flow, so I look at this random measure I get from this, and I compare its relative entropy to the original measure, and then I average it, that is actually going to be n lambda 1 minus 2 lambda sigma. And in fact, it turns out you can show that this is actually equal to the Fisher information if you have a stationary density. And in fact, you don't even need a density to define this Fisher information, but you can use logarithmic derivatives if you like. But also, one thing to see here is that this can actually be thought of as sort of a balance of entropy production. So if I let Ft be the law of my lifted process here, and I look at its relative entropy between F and the Lebesgue measure on the space, this entropy actually has a dissipation term, which is exactly the Fisher information, and a production term, which is something that at least when F goes to infinity becomes the top Lyapunov exponent. Or sorry, the top Lyapunov exponent minus 2 lambda sigma. And so this identity is actually more or less, as you send T to infinity, a balance between entropy dissipation and entropy production. Okay, I'm gonna move on from some of this I'm saying here just in the interest of time. So why is the Fisher information useful here? Well, as I mentioned, it's sign definite. It's also convex, which is particularly useful here, just like the entropy is. But it's especially useful for zero noise limits. So suppose I take my SD like this, but I have this sort of square root of epsilon or some small parameter in front of the noise. And let me also parameterize the vector fields with some epsilon as well, just for fun. Then the Fisher information identity I wrote before, I can rescale it. And because there should be now an epsilon in front of all these vector fields, I pull the epsilon out and I divide it by this. Okay, and so now I have the Fisher information is equal to these things divided by epsilon. And what this allows us to do is that we can say, well, suppose that lambda 1 over epsilon is bounded. Suppose it doesn't go to infinity. Then we have more or less, as long as we can control lambda sigma, we more or less have a uniform bound on the Fisher information. And since the Fisher information controls some level of regularity, these are derivatives of F, then we can start to actually start to use some regularity theory. So note specifically that derivatives in this vector field direction in G in the L1 norms, this is like a degenerate Sobolev W11 type norm. If G is also an L1 function, it's perfectly controlled by the Fisher information. Okay, so by simple analysis estimate. And so if I specifically use the fact that I have hypoellipticity, then I can do a lot better. So in particular, let's use a theory developed by Hörmander. So in the late 60s, Hörmander proved basically a sharp condition, especially if you work in the class of analytic vector fields, that if I take a PDE like this, which is in so-called Hörmander form, and let me just define the add x acting on y just to be this operator, the operation of x commuted with y. then I can define the Lie algebra generated by these vector fields just to be the span of all sort of Lie polynomials you can generate that belong to this list of vector fields. So this is Lie algebra, and if it spans the space, then we say it satisfies Hörmander's condition at every point x. And what Hörmander proved was that any distributional solution to the PD, if it satisfies Hörmander's condition, is smooth, C infinity smooth. And moreover, if you have this slightly stronger version, if there's a Lie algebra ideal, if that also spans, then okay, this is not fully true. Sorry, that this is true in the model version I had before, but you need some slightly extra conditions to show that it's unique. So I apologize. That's not true actually at the level of generality I'm stating here. But in fact, what we wanted to show is that, well, Hörmander, his proof, and in fact his condition implies something way more quantitative. So what we showed is, in fact, that if you have Hörmander's condition on the projective bundle, this implies that we have some subelliptic estimate. So this is just in PD language, says that if I control just partial information of f, and I know that this f solves a hypoelliptic PD, then in fact I control all regularity of f in all possible directions via some Sobolev norm, but only a tiny amount of it. So s is here is very potentially very small number related to how many brackets deep you need to go to span. Okay, but the second we have that, we have this inequality. It's quantitative inequality, but it applies locally. But it tells us that, and in fact, this estimate is independent of epsilon. This is kind of crucial here. So if we have Hörmander's condition that in a way that's uniform in epsilon, then this estimate is uniform in epsilon. And this allows us to take epsilon to 0. Okay, so this is let's say one of the key estimates that we use. And so I'll finish up just arguing a little bit about how to finish the argument. So assuming we have that estimate, let's apply it to these bilinear systems. So this x0 was our drift, and xk are the constant noise directions. Then the Fisher information that I had, the inequality, it takes this form. So the sum of the Lyapunov exponents ends up just being the trace of the dissipation matrix. And so this is the inequality we have, where we have lambda 1 over epsilon. And now we're going to assume by contradiction that lambda 1 over epsilon is bounded. And if it's bounded in epsilon, then we have a uniform regularity estimate on f. That allows us to use compactness. And in fact, combining that with some tightness estimates that come more or less for free, you get a density on the limiting projective dynamics. Okay, so this says that if I look at Euler, just the Galerkin Euler, lifted up to the projective bundle, that I have a absolutely continuous invariant measure for this dynamics. And now in dynamics in particular, it's well understood that constructing absolutely continuous projective stationary measures is a very rigid property. Okay, very naturally, because as I've sort of mentioned, projective dynamics have tons of concentrations. They have sources and sinks everywhere. And if you have concentrations, the measure wants to concentrate at those points. And so this is, you can more or less rule this out directly. In fact, you can be more specific. For the Euler equation, in fact, any bilinear model like this, you can show that if I linearize in the direction normal to the sphere, I have an exact decomposition of the linearization into a direction which is in the flow direction t, and a direction which is perpendicular to it. And what we see here is that there's a t here. And so by more or less a Birkhoff or a Poincaré/Birkhoff type recurrence argument, you can show that if I run time long enough for this thing, it eventually blows up. And because it blows up, it has to concentrate in projective space somewhere. And that violates having an absolutely continuous stationary density. Okay. The rigorous version of this is that you actually construct an almost everywhere defined Riemannian metric on the space using this measure, and show that it has, if you have an absolutely continuous measure, it has this d phi as an isometry with respect to this metric. Okay, but note that this doesn't require anything. You don't have to understand much about the dynamics. just the energy conservation actually, or the bilinear structure. Okay, so I think I'm more or less at the limit of my time. So just to show you the stuff I presented is we have a series of papers on this. So it's a few papers. This was the first one, a regularity method for lower bound Lyapunov exponents. It's applied to very general stochastic differential equations. This is the paper where we verify the condition for Navier-Stokes, which uses computational algebra. And here, if you like, is a summary paper which kind of combines all these together and is perhaps written a little bit more less technically. Okay, and I'll skip that and leave it at that.
All right. So yeah, let's thank Sam for that nice talk. With a Zoom applause. So yeah, we have a few minutes for questions. So you can either, we're a small group, so you can either just unmute yourself or you could type them into the chat. Let's see.
Maybe I can start with a maybe naive question. So you had these hyperellipticity condition on the generator. So I mean, naturally, there are also other types of generator like hyperbolic and parabolic. And so can one expect anything like similar results in such a setting?
No, I'm not sure. I mean, I think if we have there needs to be smoothing somehow, I think. So if you don't have a generator that's not doesn't have some smoothing property, I don't think, I mean, the result might be true, but these methods don't work at all. Somehow we need to show that everything regularizes everywhere in projective space, and so there are probably structures like this, and for instance, even with other types of noise, if it's not just the diffusion process, if you have a jump process or some sort of something that's not just a Brownian motion, I'm sure there are versions of it that work, but it might not be so simple, because I don't know any version of Hörmander's theorem that applies in those settings.
Thank you.
All right. I guess I had another potentially naive question, which is, you verified this sort of this Lie algebra spanning condition for Galerkin approximations for Navier-Stokes. I guess you didn't get to talk about that part of the technique that much, but it seem like those sorts of tools could be kind of further pushed to verify this condition in other situations.
Yeah, very much. So I mean, I'm not going to go into too much here, but I can tell you that like this definitely applies to other Galerkin truncations of PDE in general. So it's more of a property of Fourier multipliers. So one of the things is that like we have this H, and in fact, actually here is probably a better way to look at it. It has this coupling coefficient in front of it, which is some rational function on the lattice. And the techniques we show to generate this are that if you strongly use that is some polynomial type thing, or at least a rational function, then really, if we want to show that things generate, it comes down to a set of Diophantine equations. So there's these D's. If I commute H with H minus K, these are some quantities on the lattice. And if I show that these D's have distinct, they're diagonal matrices, they have distinct differences, then we generate the Lie algebra. And that is actually a Diophantine polynomial equation. And more or less, you can actually just compute whether that's true using Grubner bases. And it's a finite computation. It doesn't matter that we're dealing with arbitrary dimensions here, because the Fourier multipliers they live in a finite dimensional space. So this method definitely applies to other models. For instance, complex Ginsburg-Landau, other PDE type things that have non-trivial polynomial type multipliers.
Oh, thanks for that. Okay. Yeah. Are there last chance for any other questions?
One small question, if I may. Thanks. Related to Burberg algorithm and the Gröbner basis that you mentioned, would any other algorithm related to algebraic geometry also be convenient, and what are the computational properties here?
Right. So so we don't actually use the Burbacher, or if that's what's called, algorithm. It's because it's a little too slow, I think, and if you try to use it, it doesn't converge in any reasonable amount of time, because the algebraic varieties that we get they end up being 8 variables and degree 16 or something like that polynomials, and there's a huge number of polynomials to use, and so we use this F5 algorithm that is implemented in Maple. Actually, that one is the only one that seems to converge in any reasonable time. All other algorithms we've tried just seem to run on forever. So I don't know if there's that algorithm is very complicated, and that's not something I understand super well. But I don't know of any algorithm that's easily doable by hand, for instance, that would be useful here.
Okay, thanks. Thank you.
All right, so I guess we can, thanks Sam again, and then we'll move on to our next talk. So should we just take like a 1 or 2 minute break? David?